right, guys, this is our continuing in our acid-base equilibrium. She says, "Yeah, right. You have no intention of seeing me later." She said, "See you later, alligator." Common ion effect. So here, you guys, we have acetic acid. Acetic acid is what makes that's essentially the component of vinegar, which is a dilute acetic acid solution. You put it in water, it only partially dissociates. Notice it's a weak acid, acetic acid. It's not one of the 7, and so it will tend to give hydrogen. Right? It can give a hydrogen to water. The water becomes hydronium, and then we have the acetate ion, which is the conjugate base of that acid. So what happens if you add more acetate ion? When you guys agree, if you add more acetate ion, according to the Chatelet's principle, when you predict it shift to the left, so if acetate ion is added to the solution, it's going to shift to the left, and thus you're going to produce more reactants, right? So the extent of ionization of a weak electrolyte is decreased by adding to the solution a strong electrolyte that has an ion in common with the weak electrolyte. So what they're saying is, right, if we add more acetate, it's going to shift it, because remember, the weak acid is a weak acid. It already heavily favors the reactant side. And so by adding more acetate ion, it further shifts it to the left, keeping this acid disassociated. Actually keeping that acid associated, holding on to its hydrogen. So now calculate, it says, so here's a problem. Calculate the fluoride ion concentration and pH of a solution that is 0.2 molar in hydrofluoric acid. Notice that we know it's an acid, it's a weak acid, it's not one of the 7. But now notice what we're doing, we're adding 0.1 molar of hydrochloric acid, okay? So hydrofluoric acid is a weak acid, it has a Ka value, it's a relatively low because it doesn't dissociate very easily. So, what we can do is, you guys, with we can set up an equilibrium or a reversible reaction in which the weak acid partially dissociates into its ions, gives the hydrogen to the water. This is pretty typical. We can write a Ka expression in which we take the concentration of the products over the concentration of the reactant, and that's equal to 6.8 times 10 to the -4. This is all information we can get from the information given. And then let's say we had to calculate the fluoride ion concentration here, right? So initially, you think about it, you guys remember 0.10 molar HCl, that's a strong acid, that completely dissociates. So right off the bat, initially, aren't we going to have 0.10 molar if it completely dissociates? We're going to have 0.10 molar, and we were told we had, right? We were told we had 0.2 molar, what's this? Yes, so we initially have a 0.2 molar solution of this, and then you guys normally, right, wouldn't that be 0 and 0 before it dissociates? But the fact that we're adding a strong acid, we're already starting with 0.1 molar hydronium ions. And right, we have, before this dissociates, that's 0, right? So some of that's still going to dissociate, right? And we call that X. And for every X that dissociates, we're going to form X amount of that and X amount of that, right? But now you guys got to remember, hydrofluoric acid is a weak acid, so what can we usually expect about X? It's going to be extremely small relative to the initial concentration. And therefore, all practical purposes, we can essentially say it's essentially 0 compared to that, right? So you would add these two, but X is so small, we'd essentially say we just have 0.10 molar hydronium ion, 0.20 minus X, which is essentially 0, it's 0.20, and then this would be X amount, however much that dissociated with the addition of the hydrochloric acid. So then we would take those values, those equilibrium values, you guys see the equilibrium values we had at the bottom of that ice chart, and we plug it into the equilibrium expression. And you remember what X, we had X equal was the fluoride ion concentration. So we plug that in, we simply multiply that, and then we divide by that to solve for X, and we get X is 1.4 times 10 to the -3. And, right, that was our fluoride ion concentration. And remember what our hydronium ion concentration was? Remember, it was 0.10 plus X. And you guys, now this kind of confirms it. Notice now we figured out what X was, and now look, X is so small relative to 0.10. When we round it to a significant figure, 2 significant digits, we end up with what we have anyways. So if we were to get the pH of this solution, right? You guys remember the pH is, we just take the negative log of the hydronium ion concentration, which is 0.10. Negative log of that, we get the pH is 1. And what you'll notice is, remember our hydrochloric acid solution was 0.1 molar. If you just take the, and you guys remember it completely dissociates, so that means that's our H plus ion concentration because it completely dissociates. And if I get the negative log of 0.1, what am I going to get? The pH is 1. And so what do we see? The whole pH is dominated by that strong acid. So we end up with a pH of the fluoric acid solution that's simply the same pH that if we just had the hydrochloric acid. Okay, you guys, one last concept we're going to be introducing. I got to check our time. I think my phone only has a certain amount of time on it. I got to try to figure this out. So buffers, you guys, are solutions of a weak acid and its conjugate base. And so you guys think about buffers kind of, think about like a bumper. A bumper kind of prevents, massive damage to a car when it undergoes a collision. Well, buffers in the same way are going to try to minimize any major change, okay? And so if you think about it in regards to acids and bases, what do you guys think buffers would try to resist? They will resist a change in what? A dramatic change in, you might expect, pH. Okay, so here's how it works. They're particularly resistant to pH changes even when strong acids or bases are added. Okay. So a lot of times, you guys, chemists are working with buffers because we need to perform a reaction at a very specific pH because the pH level can affect chemical reactions in your body, the different, pharmaceuticals, the pharmaceutical industry that makes different drugs is definitely pH dependent. And so we would want to have a situation where a certain pH range is maintained, and we can do that with a buffer. So in this case, a buffer, we have an equaler, and you remember what a buffer is, it's a weak acid and its conjugate base. So here we have an equal molar solution of HF in sodium fluoride. So here's the idea, guys. Think about, we have a weak acid, right? Normally we have a weak acid, it only undergoes partial dissociation. The reactant side is favored, very little ions, right? So we pretty much have most of the acid. But in a buffer situation, what we do is, not only do we have the acid, but then what we do is we end up adding some of the conjugate base. And in this case, how do we do that? By adding sodium fluoride to this solution. So if you add sodium fluoride to the solution, wouldn't you guys agree? Whereas before, when it was just hydrofluoric acid, very little fluoride ions. But if we in turn add sodium fluoride, which would provide our fluoride ions, now we're adding the conjugate base. So in a buffer situation, not only do you have the acid available, but you also have a base available. And therefore, whenever you add an acid or a base, let's say we add an acid to our buffer solution, what do you think that acid's going to be able to, what's it going to react with? Won't it react with our base? And so the effect that the presence of the base will react with the acid. And you guys got to remember this, a basic acid-base reaction. When you think acids, think H+. When you think bases, think OH-. Whenever you have H+ or OH- combined together, they form water. They neutralize each other, right? Acids and bases neutralize each other. So the presence of the base would neutralize the addition of extra acid. Whereas normally you would add a whole bunch of acid, and what would you expect? Right? The H+ concentration to shoot up, and thus the pH to drop dramatically. But that's not going to be the case if you have a base present to combine with the acid and then neutralize and take the additional H+ ions out of solution. Likewise, if I was to add a base, normally if you guys, right, if I were to add a base, now I still have my acid present, and now the acid will interact with the base and thus minimize the addition of the base. So add sodium hydroxide, what happens? So let's say you add sodium hydroxide. So I'm adding sodium hydroxide, right? What's the main thing in sodium hydroxide? You guys know sodium hydroxide is pretty much just gonna completely dissociate. What's the thing I'm interested in? It's the OH-. Remember, that's what sodium hydroxide is, a strong base. So then you're thinking about, normally if I added a strong base to a solution, Now all of a sudden I've dramatically increased the OH minus concentration, which lowers the H plus concentration, right? Because the OH minus would take a bunch of, would combine with hydrogen ions, pulling those out of solution. Thus, the hydrogen ion concentration is lower, the pH is gonna shoot up, right? You add a base, the pH is gonna shoot up. But in this case, if I add it to a buffer solution, what's that OH minus ion going to react with? It's gonna react with the presence of the acid. And what's gonna happen when you have the HF and the OH minus? Isn't the hydrogen from the acid gonna combine with the OH minus and form water? And so you guys see, essentially, the presence of the acid reduces the impact that the addition of the hydroxide ion would have, and thus the pH is not going to change nearly as dramatically. Similarly, if an acid is added, what would happen? So that's when we added sodium hydroxide. Now, if you added an acid, right? So if we had an acid, we're thinking H plus. So what would the H plus interact with? What would it react with? Wouldn't it react with the conjugate base? So what these will come together and form HF. And so you guys see the presence of the base takes out the additional H plus, which would normally cause the pH to drop dramatically, but now it combining with the conjugate base pulls that out of solution, and therefore the pH drop is going to be much less than it would otherwise be. Okay, let's see what it look like.
A buffer is an aqueous solution containing both a weak acid and a weak base that are a conjugate acid-base pair. The buffer shown contains the weak acid acetic acid and its conjugate base acetate. These species are dissolved in water. Water molecules are not shown in this animation to draw focus to the buffer component. A buffer solution has the ability to resist changes in pH upon the addition of small amounts of either acid or base. Choose to add a strong
So you guys
acid
see,
or a strong base.
typically a
to the
buffer,
by
we're going to
clicking
have
one of the
equal
buttons.
amounts of a weak acid and its conjugate base. That's like right here. Here's the weak acid, and we have equal amount of the conjugate base. So now if we add a strong acid, we're going to add a whole bunch of H plus ions.
Only hydrogen ions,
So
H
normally,
from the hydrochloric
The pH
acid
would
is
shoot
shown
down
here
with
in the
all this
solution.
addition of the H plus
Chloride
ions.
is
But
not
look,
shown
what's it going to
because
react
it
with?
is a spectator
It's going to
ion.
combine with the
It does
acetate
not
ions
participate
here.
in the reaction. The strong acid H plus reacts with the base component of the buffer acetate, CH3COO-, producing the acid component of the buffer acetic acid,
So that way,
CH3COOH.
used up all the H plus.
The buffer has resisted a change in pH by removing strong acid H plus from the solution.
Okay, guys. Unfortunately, for time's sake, I'm going to move on just because, like I said, I think my phone only has a little bit of charge. Okay, consider the equilibrium constant expression for the dissociation of a generic acid HA. So we have HA with water, it gives a hydrogen to water, you form the hydronium ion. Okay, so that's our Ka value. Okay. Rearranging this slightly, so what we're doing is we're simply taking this. Okay, so now it's just going to be algebraically manipulated. Okay, so look, so we just kind of make it look a little different. Then you guys remember, we can do anything to an equation as long as what we do to one side we do to the other. We take the negative log of both sides, and we get negative log of K is equal to negative log of H0 plus. When you multiply, you can add it. And then, what is the negative log of Ka? That's called the pKa. The negative log of the hydronium ion is the pH, and then this is ultimately what we end up with. So you guys, here's in purple, this is what you guys need to write down. This is the Henderson-Hasselbalch equation. That is the equation. Typically what we use that for is that will be used when we decide, like a chemist is deciding what pH they need a buffer at. So what you would do is you would use remember you're going to use a weak acid and its conjugate base. So what you would do is you're going to use a weak acid such that its pKa is very close to the pH. And here's the reason why. Because think about it. Remember, we're going to use equal molar. So let's say we use 1 molar of a weak acid and we use 1 molar of its conjugate base. What's 1 divided by 1? Wouldn't that be 1? And the log of 1, if you take the log of 1, you punch in your calculator, you get 0. And so what we'll find is that the pH of the buffer is equal to the pKa. So what this allows us to do is choose a certain weak acid with a certain Ka value that has a pKa essentially equal to the pH of the buffer that we want. Okay, so this is typically what you use Henderson-Hasselbalch for, is to determine the pH of the buffer. Okay, so we want to know what's the pH of a buffer that's 0.12 molar in lactic acid. You guys see it's this big old funky acid, but it's just this hydrogen that it gives up, so don't worry about that. And then we have 0.1 molar sodium lactate. Lactate is the conjugate base. You guys remember the conjugate base is just the same thing without the hydrogen. We have the Ka for lactic acid is 1.4 times 10 to the -4. So let's say we wanted to make a buffer with lactic acid and sodium lactate. We want to know what is going to be the pH of this buffer. Well, we use Henderson-Hasselbalch to get the pH. I use the pKa. Remember what the pKa is? It's just the negative log of my Ka, and that was given. That's going to be given for a certain weak acid. And then I take the concentration of my base. My lactate was 0.1 molar, and my lactic acid was 0.12 molar. And what you'll see is, you'll plug that in. So you just press the log button and then you subtract it. So this would normally be, this is the pH of my, or this would be the pKa of my acid, okay? But then you see it's slightly altered. You guys see, because in this case, I didn't use equal amounts. If I used equal amounts, right, that would be 1, and the log of 1 is 0, and so it would just be 3.85. But it gets slightly altered because they're not equal molar, and we see that the pH now of this buffer solution is 3.77. pH range is the range of pH values over which a buffer system works effectively. Got a few minutes. Man, it's best to choose an acid with a pKa close to the desired pH. As a chemist, if you have a desired pH, you're going to choose a weak acid that has the negative log of the Ka, which is called the pKa, that's close to the pH value. Okay. When strong acids or bases are added to a buffer, it's safe to assume that all the strong acid or base is consumed in the reaction. Okay, so now this is where we're going to, so here's the thing. So you have a buffer, you add a strong acid or base, determine how the neutralization reaction affects the amounts of the weak acid and its conjugate base in solution. So here's the idea. Hopefully you guys can see. Right, we have equal molar, 0.3 molar acetic acid, 0.3 molar sodium acetate. So we have the weak acid and the conjugate base, right? It has a certain pH. Okay, in fact, that pH would just be equal to the pKa, much like we just did before. But now, look what happens when we add 0.02 moles of OH minus. That's a strong base, right? That's our base. Notice what you would expect. You'd expect the base to react with the acid. All of the strong base, you would expect to react. So what did we have? We had 0.02 molar. We had 0.3 molar acid minus 0.02 of it, which is going to combine with the base. You guys know the acid combines with the base to form water. So now instead of 0.3, we're going to have 0.28 molar of our acetic acid. And then, you get, right, when that acetic acid reacts with the base, right, when it reacts with the base, the hydrogen and the OH minus form water, and then what else do we have left? We have the acetate ion, that's what's left. And so we see the acetate ion is going to increase by 0.02. So whereas before we had 0.3, but we had 0.02 that reacted, so now we have 0.32. So look at how it's going to work in the ice chart. And then it says, so it's 2 steps. Then we use the Henderson-Hasselbalch equation to determine the new pH of the solution. So we first see what effect is going to adding the strong base and the strong acid have on the initial concentrations. Then we use the equilibrium, the new concentrations in the Henderson-Hasselbalch to get the pH. So a buffer is made by adding 0.3 moles. So this is kind of going over what I just kind of summarized. The pH of the buffer is 4.74. Calculate the pH of the solution after 0.20 moles of sodium hydroxide is added. Once again, normally if you add a strong base to a solution, the pH is going to shoot up, right? Because what you're doing is you're making it more basic. But what we're going to see with the buffer is it's going to resist that, and it should minimize the impact it has, and we'll see. So we have acetic acid, right? When you added the hydroxide, what you're going to have is the OH combines with the hydrogen to form water, and then you're forming acetate. So here's what we have before the reaction, right? We have this moles, and then we add this. But then after the reaction, check out what we have. All of this is going to react with this, and so therefore we're going to have 0.02 less of this because 0.02 of it reacted with the hydroxide. And for every 0.02 moles that combines with acetic acid, we form extra 0.02 moles of acetate ion. And then all of the hydroxides used up. So then we're going to use these values here in our ice chart. Or I'm sorry, not in our ice chart. I'm sorry. Then those are going to be the concentrations that we are going to use in our Henderson-Hasselbalch equation. So now this is the concentration of my acid, and this is the concentration of my base. Right? You guys see the concentration of the base over the concentration of acid. Look at your Henderson-Hasselbalch that you guys wrote from previous slides. And so this was the initial pH, and we see the addition of the base alters the pH, and as expected, what happens to the pH? It goes up. And notice, you guys, whereas before we've been 4.74, notice it only went up very slightly. That's the effect of a buffer. It minimizes the impact of acids and bases. Whew. Guys, I know it's tough. Hopefully we'll clarify some things when we review these things, but attempt it nonetheless. All right, guys, till next time.